Okay, so like I said, we're going to continue on here. The lab that's scheduled for today is study assignment B, I believe, and it's Lewis structures, it's molecular geometry, polarity, and a hybridization, a bunch of stuff. So we're gonna wrap up here this chapter, which we're pretty close to wrapping up. We're gonna get into a little bit of chapter 4, and that way you can at least make a good dent in the study assignment there. And we'll talk about when it'll be due and next week's lab as well. All right. So to sort of finish up this chapter here, we were just talking about the exceptions to the octet rule. And as I mentioned before, again, probably the expanded octet is definitely the one we're going to see a lot in this class. And as we mentioned, again, anybody sort of around sulfur there on the periodic table and below has the ability to do that. Also into the, you will see some noble gases as well being able to do that, and some Lewis structures that you'll be asked to draw. They can go over that again, the ones kind of with sulfur and below on the periodic table. So why don't you take a few minutes here and draw up these probably expanded octets and see what you get for your Lewis structures here. Okay, let's take a look here. So we'll start here. We'll just follow our normal sort of pattern. So that's going to be 7 for the bromine, 5 times 7 there for the fluorine. That's 42, I believe. In this case, between bromine and fluorine is obviously more electronegative, so the bromine should be in the middle. Again, we will attach our fluorines around, and you can lay that 5th one wherever you like. We're going to do our same sort of deal, single bond to everybody. So that is 2, 4, 6, 8, 10 electrons. We got 32 more to go. They're going to go on the outside in pairs. So that is 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, and 30, if I count it right there. So at this point, we have now placed basically 8 times 5, right? Has 40 electrons. We still have 2 more to go. So just like we did previously, they will go on the center atom as a pair of electrons in this case. Any questions on that? We know as well, just looking at the periodic table, we see bromine below sulfur. So it has, again, the ability to go above 8 and do the expanded octet. Any questions on that one? Coming here to our guy here, that's going to be 7 plus 3 times 7. It's going to be 28 electrons. In this case, once again, chlorine being the least electronegative in the center. We're going to do fluorine on the outside. We're going to do our single bond to each. So that's 2, 4, 6 electrons. 22 more to go. So that is 2, 4, 6, 8, 10, 12, 14, 16, 18. At this point, we have attached 24 electrons. We have 4 more to go. They would also, again, go on the central atom as dots. You, again, do not want to start double bonding or triple bonding until you have distributed all the electrons. Yeah, so that's how we get those dots on the central atom when we need them. Any questions on that there? Everybody's good in terms of 8. And then once again here, chlorine going above 8. And lastly here, xenon, which is our noble gas there, that's actually group 8. Plus 4 times 7. That's 28 and 8, 36. Something like that. Xenon would go in the center. By the way, electronegativity value for noble gases is 0. Yeah, they really don't want to basically do anything. So they basically have no electronegativity. We'll do our fluorine around, doing our single bond here. And now that's 2, 4, 6, 8 electrons. So we've got a bunch more to go. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. At this point, we basically have 8 times 4, which is 32 electrons on there. Once again, we still have 4. And again, those will find its way to the center atom as pairs of electrons. Any questions on these? Are all expanded octets, obviously, here that we ended up with. Any questions on drawing that there? All right. So again, obviously, I would say in our case, or in most cases, you should follow the rules we talked about in terms of drawing Lewis structures, and maybe not go expanded and double bind and triple bind out of the box, but sometimes you need to do so, as you can see in this case. Think SO4 2 minus, right? And you had to draw the Lewis structure for it. SO4 2 minus. If you follow our sort of steps, you will end up with this structure here. Again, if you follow sort of our steps and all that good stuff. Now, I'm sure nobody would do this, but if you just Google the answer, perhaps, right? And maybe if you looked online and you Googled it and all that good stuff, and maybe you did this in your previous class and your instructor probably knew you did that, by the way, you might come up with this structure here. By the way, a teacher would know you did that because probably in the previous class you didn't do expanded octets, and there should be no reason for it to have double bonds on it. So they probably know you just looked it up on the computer. It is perfectly fine in that situation as well. It's a perfectly good structure. Actually, we talked about this as well when we talked about formal charge, right? So if we did our formal charge, for example, on our single bonded oxygen, that would be 6 minus 6 minus 1/2 of 2 is a -1, right? So that's again valence electrons in the atom, number of non-bonding electrons, half the number of bonding electrons. That would give me a -1, -1, -1, -1. And if I did my sulfur, which looks like this, that would be 6 minus 0, as there's no dots, minus 1/2 of 8. And that's going to give me a +2 happening there in terms of this structure for our sulfur. We add all that together as +2 in the middle, -4 on the outside. That's a -2 overall, which equals the charge, which is all good. Now, if I did the formal charge for the bottom structure, which you might have Googled, you would end up with obviously the same for our single bond, 6 minus 6 minus 1/2 of 2. Gives you a -1, so we have -1, -1. We would have a double bonded oxygen as well, which would be 6 minus 4 for our non-bonding electrons, minus 1/2 of 4, which is 0. And now for our sulfur, which will then end up looking like this in that second structure, that's going to be 6 minus 0 minus 1/2 of 2, 4, 6, 8, 10, 12. Which will give me 0. Based on formal charge, which is actually the better structure. In this case, it actually is the Google one that's the better structure in this case, even though you shouldn't have ended up that way. So if you were drawing this based on formal charge, this one actually is a better structure, which is why it's on the internet, because it minimizes the formal charge, obviously, to the zeros and -1s. But if you just follow the regular rules of sort of drawing a Lewis structure, you would end up with the top one. Again, this is a situation like we talked about. You could use formal charge if you wanted to pick between structures and maybe pick a better structure based on formal charge than another. Any questions on that there? Yeah. Okay. All right. So chapter 4, truthfully, is just a continuation of basically what we've been talking about. So we've talked about obviously drawing Lewis structures, expanded structures, bond polarity. Here in this chapter, we're going to cover molecular geometry. We're also going to cover molecular polarity, and we're going to talk about some hybridization models and stuff of that, of bonding. So kind of a continuation here. So let's start with geometry. When we talk about molecular geometry, it does refer to the three-dimensional sort of arrangement of obviously the atoms and the molecules. The molecular geometry cannot be predicted by necessarily the Lewis structures, but if you know basically how many electron pairs there are around the central atom and how many bonds there are, which from a good Lewis structure, you'd be able to determine. You will be able to predict is sort of molecular geometry. And when we talk about geometry, we're actually going to talk about two types of geometry and two types of names. One is going to be referred to as the electron pair geometry, which for my purposes here, I'm just going to abbreviate EP for electron pair. The other one is the molecular geometry. And sometimes people just refer to this as the shape. And for our purposes here in this lecture, I might just refer to it as MG for molecular geometry. These are names that describe, as we will talk about, pretty much how the electrons are arranged around the central atom in terms of electron pair geometry, and the name for the molecular geometry talks about the overall shape that takes into account how many electron pairs there are, what types of electron pairs, what types of bonds are present in these things. As we will see in certain cases, these names will be the same, and in other cases, they will be some different names that occurs because of the types of electrons that are present. Now, the best approach that we take is, or the approach that we do take here, is the idea that we are dealing with electrons which are negatively charged. And when you're making bonds and you got electrons around everything, do they really want to be near each other since they're all negatively charged? They actually do not want to be near each other because things that have the same type of charge really are repelled by each other. The problem is they can't really escape because, frankly, they're in a bond and the other electrons are stuck onto it by the attractive force to the nucleus. So, what ends up happening in this sort of model is the electrons really, in all cases, will try to get as far away as possible from each other. Again, they can't really escape because they got to hang on there because they're bonded. So they'll start trying to move away as far as possible from each other. And what that ends up doing, if you just think about it, if you have a bonding pair of electrons, as those bonding pair of electrons start to move, so does the atoms that are connected with those bonds, right? They start to move with them. If you have non-bonding electrons, they will start to move. And as those non-bonding electrons get near something like bonding electrons, they're going to try to get away from each other as far as possible. And that ends up causing the actual shape of the molecule to really change, depending on, really, as we'll talk about, are there bonding electrons present? Are there non-bonding electrons present? Is there a little bit of everybody present? And depending means that they really do not want to be near each other. So if we have electrons which are negatively charged, they definitely don't want to be near each other. They're going to repel each other. But because they are held within a bond, they really cannot truly escape each other. So what they really try to do ultimately is they try to get as far away as possible from one another. And as they are trying to sort of escape each other and get away from each other as far as possible, what ends up happening, obviously, if you have electrons involved in bonds, is those atoms start to move with those electrons, right? And what that provides is some different shapes or geometries for our molecules as those electrons ultimately are trying to basically escape each other. So that is what is known as VSEPR here, which stands for valence shell electron pair repulsion models. And it's really divided into two sort of categories. One category is a central atom that has no lone pairs. And that means when you draw that central atom, you basically have bonds, you have no dots, basically, on your Lewis structure. And there are atoms or molecules, molecules that have lone pairs on the central atom. So when you draw them, they got at least some dots happening there, which are non-bonding electrons. So when we do geometry, and only when we do geometry, there's two really important things. And really the first one is kind of most important, which is we treat all double and triple bonds as though they were single bonds. And they count as single electron pairs and they count as single bonds. Now, one of the ways that you can sort of do geometry and probably the best way for most people to do geometry is to look at how many electron pairs there are around an atom and how many bonds. So those are kind of the two things that you look at. And usually you do geometry for the central atom. And the central atom is always the one in the middle and is the most important in terms of geometry. And that's where we apply geometry to. So if you have a single bond, if you got a double bond, or if you got a triple bond, they all count as one electron pair and one bond. So again, that's just for geometry, and that's really important here. The other part there is if you can draw a resonance structure for a particular compound like we did earlier, you could apply this geometry to all the resonance structures. And in most cases, pretty much the resonance structures will end up with the same geometry along the way. Now, when we talk about geometry, we really will talk about kind of two types of geometry once we get kind of going here. The two types of geometry we're going to talk about is one is what is referred to as the electron pair geometry. And the electron pair geometry basically describes, kind of like the name, it describes how the electrons are arranged around the particular atom you're looking at, the central atom as well. Now, the other type of geometry that we're going to talk about is the molecular geometry. And that is also sometimes just generically called the shape of the molecule. And what the molecular geometry or the shape of the molecule is as a result of how many bonds there are, how many non-bonding electrons there are, sort of what's around it, the actual overall shape of the entire molecule. Now, what we will see is in certain cases, these names will be the exact same names. And in certain cases, they will be different names depending on sort of what's present and what's not present. So as we go through it, especially when we get into 3 or more atoms, that's really where these two geometries kick in. There will be, again, an electron pair geometry sort of name and a molecular geometry name. So let's start with really the simplest atoms you could pretty much ever have, or molecules you could ever have, and those are diatomic molecules. And diatomic molecules, obviously, as we know, hopefully, is basically, as we were talking about before, basically only 2 atoms, right? So we have only 2 atoms involved. And as you perhaps know, right, maybe got a model kit I stole from somewhere that was in the lab, I think. I don't know, we'll see. If you just have 2 atoms, the only way you can connect them is a straight line, right? No matter what you do, that is the only way you can kind of put 2 atoms together is a straight line. So if you have a diatomic molecule and you're asked what is the geometry, you should put linear down and move on, right? Don't overthink it. There cannot be anything else. By the way, it doesn't matter if it's a single bond. It doesn't matter if it's a double bond. It doesn't matter if it's a triple bond. Doesn't matter if it's the same elements or different elements. It will always be a linear approach. So, for example, I think they got them in here, maybe. Oh, I'm gonna try it, maybe. Maybe I could get it to do it on this guy, maybe. Let's see. So if I have a single bond, maybe I'll do it. And I have a double bond, still straight line, right? Doesn't matter. And for the trifecta here, if I go for a triple bond, doesn't matter either, still a straight line, right? So 2 things, doesn't matter what it is, straight line. By the way, let's undo our triple bond, small distance between them, yes? I take it away, distance gets bigger, right? Take away a bond, and an atom falls off. That happens sometimes, you know. And obviously our distance gets larger, right? As we talked about earlier, right? So every time we put a bond on, everybody gets moved towards the center of the electron density. Distance between the atoms gets smaller as you go through it. All right. Fun with model kits. I know, it's good. All right. So let's talk though about when we get to 3 or more atoms. And when we get to 3 or more atoms in a molecule, we do have to look at 2 things. As I mentioned before, it is always about the center atom. So you always want to look at the center atom when you're doing geometry. And there's really, again, 2 things that you essentially want to count, which is the number of electron pairs around that central atom and the number of bonds. So those are really the 2 things that you kind of want to look at and count. So let's take a look at our first sort of example here, 3 or more. This is beryllium chloride, which is an incomplete octet. And if we count up what we want to go to the center atom and we want the number of electron pairs. So again, if we count up the number of electron pairs around the central atom, in this case, we see 1 and 2 electron pairs. So it has 2 electron pairs. And the number of bonds in this case would also be 1 bond and 2 bonds. Now, remember we talked about the idea that there are 2 types of geometry names. So the electron pair geometry, and from this point on, I'm just going to call it the EG for short, is something with 2 electron pairs. It has to do with the total number of electron pairs around central atom is going to be linear. So what does that mean? It means that when you take an atom and you put it together, what's going to happen is these bonding electrons here and these bonding electrons here, they essentially want to get as far away as possible from each other. So the best way that they could do that is they're just going to go on opposite sides of each other. That is as far as they could get from one another. And that is going to give you a linear geometry for the electron pair geometry. Now, the molecular geometry, or the shape, which I'm going to call from now on just MG for short, is also going to be linear. Now, why is it linear? It's linear because as those electrons are moving away from each other, they're hanging on to those atoms, right? So as those electrons move, so do those atoms, and they also end up in the exact same location as those bonding electrons, linear away from each other with a bond angle of 180 degrees. That's essentially as far as possible as they can get from one another, and that will get you that 180-degree bond angle. And 2 electron pairs and 2 bonds will always give you that linear molecular geometry and also the linear electron pair geometry, again, because our bonding electrons are moving our atoms with it. So everybody's going to move basically the same. The next sort of geometry that you may be familiar with is also here, for example, a incomplete octet, which is boron trifluoride. And again, we're going to look at the boron in the middle. And the boron in the middle, which is our central atom, we're going to first count up the number of electron pairs. And once again, it has 1, 2, and 3 electron pairs. Now, something with 3 electron pairs, the electron geometry name is trigonal planar, or sometimes people call this triangular. So what happens in this particular case? What happens in this particular case is we have electrons now, 3 pairs of electrons, which means this electrons here need to keep distance from each other. These guys also got to keep distance from each other. But now these electrons don't really want to get too close from each other either. So they're going to basically keep that same distance. And what ends up happening is when we look at how many bonds it has, 1 bond, 2 bonds, 3 bonds, it creates a molecular geometry that's also trigonal planar. It basically creates a equilateral triangle. And once again, the geometry, both the electron pair geometry and molecular geometry, are going to be the same because each of those electrons are bonding electrons. So as they move, so do the atoms, and they end up in the same location. And I could maybe represent it like this here, but don't lose my carbon atoms, maybe. Let's see here. I could do it. Actually, I could probably still use my work. To this up there. Like that octet's got more options. I like it. All right, so we got something like this, right? So they're going to try to keep distance from each other. They're going to try to keep distance from each other. They also don't want to get too close to each other. Again, we have all bonding electrons here, which as they move, so there's the atom, right? So the atom moves with them, makes this triangle type shape, as you can kind of see here in this case. Bond angle 120 degrees there is the bond angle here. And you can dump it upside down like it's doing a handstand, I suppose. That's well, very good. Any questions on that one there? Now, continuing on here, the next sort of thing that you might have seen previously as well is something that we see with methane, which again, if we look at our central atom here, and the number of electron pairs around our central atom is 1, 2, 3, and 4. Something with 4 electron pairs has an electron pair geometry name of tetrahedral. Or if you're old like me, tetrahedron. Not too many people roll with that too much these days, but we'll go with tetrahedral. So again, if we look at the bonds in this case, we got 1 bond, 2 bonds, 3 bonds, and 4 bonds. And the number of bonds here is going to be 4. Now, by adding the extra atom in that case, everybody's got to keep their distance. So again, we got these electrons trying to get away from each other, these guys, and again, these guys can't get too close. So what ends up happening in this case is so we end up with something like this, which is our tetrahedral arrangement. Kind of triangular on the faces, and it's almost pyramidal there on the bottom. And again, what happening here again is they're trying to keep our distance. They're trying to keep the distance. Everybody's trying to keep the distance from one another. And we end up with that tetrahedral arrangement in this case. That bond angle, by the way, is 109.5 coming through there, which is our bond angle for our tetrahedral. Any questions on those there? So up to there is probably ones you've seen before. That's typically what you covered maybe in the 100, and some of those guys with some non-bonding electrons, which we'll get. But we have some expanded octets happening. So with our expanded octets, such as this guy right here, PF5, we again can look at our central atom, which is our phosphorus, and the number of electron pairs in this case is going to be 1 electron pair, 2 electron pairs, 3, 4, and 5 electron pairs. Now, something with 5 electron pairs obviously is our expanded octet, and our electron pair geometry is going to be triangular bipyramidal. Once again, in this case, in terms of the number of bonds, it's got 1, 2, 3, 4, 5 bonds. So our molecular geometry is also going to be triangular bipyramidal. Once again, they are the same, as obviously these are all bonding electrons. So as we talked about previously, as the bonding electrons move, so do the atoms. So if I were to grab this and pop them in here, maybe borrow some of those there, maybe. At least my hydrogen. There, 5 right now. All right, so we have a bond angle of both 90, right about there, 90. And we also have 120, which is like our triangle that's happening right there through the center. I'll tip it this way. That's our triangle through the center, coming through this part here, here, and here. It's our 120 degrees, and our 90 degrees coming off the top. So right here, you maybe see it here. That is our triangle, just like we see in trigonal planar. And again, our 90 degrees coming off the top of it here. So if I rotate it, you can maybe see it. This is the triangle and our 90 degrees coming off the top. So we actually have two bond angles in this particular rotation of phosphorus. And obviously I didn't put all the fluorines on there, but there would be fluorines on each of those guys at the end. The last sort of geometry that we come across here with the expanded octet is one where we have an SF6. And if we look at the central here with a number of electron pairs, it's going to be 1, 2, 3, 4, 5, and 6. Something with 6 electron pairs is the electron geometry name of octahedral. And it has, in terms of bonds, 1 bond, 2 bonds, 3 bonds, 4 bonds, 5 bonds, and 6 bonds. And something with 6 electron pairs and 6 bonds, the shape or molecular geometry is also going to be octahedral in this case. And again, if I steal maybe a sulfur here, we will end up with a bond angle of about 90 degrees. So we go here, pop them in. Try not to roll my phosphorus off the bench here. And one more for good measure, maybe. So this is our octahedral arrangement. Again, 90 degrees sort of happening through there. And again, obviously our expanded octet having 12 electron pairs around the sulfur. Obviously we would have atoms at each of those locations in this example here. And again, giving you your 90 degree sort of geometry that's happening there. Any questions on those so far? Now, up until this point, what we have seen is both the electron pair geometry name and the molecular geometry name are exactly the same. And again, they are exactly the same because when we look at the Lewis structure, for example, there is no non-bonding electrons there, so there's no lone pairs. So as I've been talking about, the only type of electrons we have present are bonding electrons. And again, since they are bonded to those atoms, as they move, so does the electrons move with them, and the atoms move together. So you will always end up with the same name. So if you draw a Lewis structure and you have no dots on the central atom, both the molecular geometry and the electron pair geometry should be the same name because you have only bonding electrons present. What happens when we start introducing non-bonding electrons, things get a little bit more dicier because we are now introducing some different types of electron and electron interaction. Up until this point, the only type of electron interaction we have are bonding electrons near bonding electrons. And in the case of electrons versus electrons, that's like your best situation. It's almost okay and manageable. They're okay with that. But once you start introducing the non-bonding electrons, are your dots on your Lewis structure when you draw them, we get non-bonding electrons interacting with bonding electrons. We also can have non-bonding electrons interacting with other non-bonding electrons. In addition, and the only way that we could have non-bonding electrons around the central atom is we will also not have a bonded atom there, right, in that slot. So we will also lose that atom. And what that does is it gives people a little bit more room to move around. And what we actually see once we start introducing non-bonding electrons is it is between the electron geometry and the molecular geometry names, it is the molecular geometry name that changes. The overall shape of the molecule will change. This will stay the same. So if you still got 3 electron pairs, it's still going to be trigonal planar for the electron geometry. You still got 5 electron pairs, doesn't matter if they're dots or lines. You'll still have triangular bipyramidal. But what happens because of those non-bonding electrons and the repulsion and the space that's left by the atom not being there, the overall molecule kind of turns a little bit more than it's able to do with the atom there, and you'll get a different shape or molecular geometry that occur. So what type of repulsions can we have? We could have bonding near bonding, which in our Lewis structure is lines near lines, right? So that's like the best situation. The next best situation is we got some non-bonding electrons, which are dots near lines. That's getting not so great, but still all right. Worst situation ever, non-bonding electrons near non-bonding electrons. The only way you get multiple non-bonding electrons near each other is you're missing a lot of atoms, and that gives them a lot of space to get away from each other, and that's going to cause the overall molecule really to start to change the shape from where it was when you had all those bonding electrons in there. So let's take a look at some of these here. So the first example will be sulfur dioxide, which we drew earlier. And sulfur dioxide, if we look at the central atom here, and I'll draw it maybe a little bit bigger here so we can kind of see it here. And I'm not going to draw the dots on the outside, but if we look at our central atom, number of electron pairs in this case is, how many electron pairs do I have? Doesn't matter if they're lines or dots. I got how many? Got one electron pair here. I got one electron pair here. And my double bond counts as how many? Just one, yeah? So remember, double bonds, triple bonds, single bonds, they all count as one electron pair and one bond. So that is 3 electron pairs. So we already know, we already have seen something with 3 electron pairs. The electron pair geometry is going to be trigonal planar. But what we now have in terms of bonds is one bond there, and once again, our double bond only counts as one bond, so we have only 2 bonds here. So what happens is what we have are these non-bonding electrons, which definitely don't want to be near those guys, nor does this guy want to be near it. So that's going to cause these oxygens to move downward away from them, and we're going to get a molecular geometry that is known as angular. And sometimes people will call it bent angular. And nowadays, people just call it bent, which they really shouldn't, but we'll talk about why they maybe shouldn't. But you will end up with something like this where the oxygens will find their way away from the non-bonding electrons. But remember that these oxygens can't get too close to each other either because they still don't want to be close to each other. So you end up with this angular sort of shape. And we've got their sulfur. I can maybe do it with this guy here. Yeah, probably. Yeah, that would be that guy there, maybe. Maybe pre-auctioned it up here. I like it. Maybe it'll work here. This will do it. Maybe here. Oh, if I can get it. Maybe. So you'll get this sort of angular type of shape that will happen here. And again, it's not a very strong sort of angle, but we'll end up with here. And obviously we still have, and I'll just use a stick up here. We have our non-bonding electrons as well, you know, up in this area as well. But we have our angular sort of shape like that, sort of almost like a V, but not a strong V. And again, what happens is these guys do not want to get too close to each other, and they're definitely trying to get rid of those, away from those non-bonding electrons, which are up in obviously this region. So again, it's causing the overall shape of this molecule to go away. That is because we have non-bonding electrons up here rather than a bond like we had with the trigonal planar geometry that we see up here. The bond angle on this one is based on the electron pairs. So the bond angle is less than 120 degrees. So when you do bond angles, it's always based on the electron pair geometry. And in this case, it still has 3 electron pairs. It's a little less than 120, again, because we have non-bonding electrons up there rather than bonding electrons in terms of our angle. Coming through here to the next one, we have a central atom like an NH3. And if we look at our nitrogen here, the number of electron pairs is going to be 1, 2, 3, and 4. Remember, when you're counting electron pairs, doesn't matter if they're lines or dots, it's just total electron pairs. That is 4. We already know that if we have something with 4 electron pairs, that's going to be tetrahedral for our electron pair geometry name. Now, in terms of bonds, we have 1 bond, 2 bonds, and 3 bonds. So the number of bonds here are 3. So what happens in this case is very similar. We got these non-bonding electrons up there, and that's going to cause these guys to move away. But we do have this third sort of atom down here that they cannot get too close to one another as well. And it creates a geometry that's known as trigonal pyramid, or pyramidal if you like. And again, it kind of makes a triangle up on top and this pyramid type shape on the bottom. And let's see here, let me grab that there and just go this way here, maybe. Some nitrogen, I have nitrogen, I think. Which colors? That's blue. Well, still a blue. So if I get in there we go. So we have basically NH3 here, and makes this sort of pyramidal shape on the bottom, and we do have, already have like non-bonding electrons. Some model kits have like little things up there. These would be like our non-bonding electrons. Again, making a sort of like a triangle on top and this kind of pyramidal type shape towards the bottom here. And that's going to give us a bond angle that's less than the tetrahedral one, less than 109.5. So the bond angle here is less than 109.5. And you can see here it's actually 107 or so in NH3 is the actual bond angle for this particular one. Another example of some lone pairs, one that you've probably seen before, is our friend water. And by the way, before we get to water, let's just go back to this guy. By the way, this is trigonal pyramid. And previously we saw trigonal planar, yeah? And that is something different, right? That's 3 electron pairs and 3 bonds. There is a difference, yes? Don't make me choose when you're on an exam or quiz. Don't just write trigonal, yeah? And let me choose, because I'm going to choose an X, yeah? So I failed chemistry, so you choose. You got to choose trigonal planar, trigonal pyramid. They are different. Can't just put trigonal. Or my second favorite answer, which is trigonal, very confident. P, very confident, not so confident. The rest of the writing, like clearly that says planar. I mean pyramid. I mean, which one is it? It's clearly that one, right? So make sure you choose. Don't just do any of those things. They are different, obviously. All right. So now back to water here. We're going to go with our central atom here. And the number of electron pairs in this case is going to be 1, 2, 3, and 4. And our number of bonds in this case is going to be 1 and 2 in this case. So that would be 2. And obviously something with 4 electron pairs still has an electron pair geometry name of tetrahedral. In this particular case, much like ammonia in the previous one, we actually have all the interactions happening at once here. We have bonding electrons near bonding, we have non-bonding near bonding, and we now have non-bonding near non-bonding, which definitely do not want to be near each other. So what's going to happen because of these non-bonding electrons here, they're going to try to go as far away as possible while trying to keep these guys away from each other. And also these guys got to kind of keep away from each other. So you're going to try this balancing act that we get this molecular geometry name known as bent or V-shaped. Hence why we are going to be going with angular on that one for SO2 to distinguish it from this one, which is bent or V-shaped. And the reason for that has a lot to do with the bond angle that is different. So I'll just grab that guy here, maybe still a couple of these here. So this obviously is our water. Again, we have our non-bonding electrons, which are essentially, again, we'll just use these sticks to represent those. So those are our non-bonding electrons up here, trying to get away from each other, also trying to keep the distance from here, and these guys can't get so close. Why are we going to go with bent or V-shaped versus on this one and angular on the other? You could probably see it in the angle of those two, yeah? This is a much different angle than this guy, right? More like a 120 on this guy. This again is more of a 109 angle. So there is a difference, but I'll be honest with you, even your lab book and other places, they do use bent a lot for this angular one. But for us in here, we're going to use angular for it so we understand which one's which. But there is a very big difference, as you can see, just with the models of the bond angle that we got. This one, again, is going to be based off of the tetrahedral bond angle, while the angular one's based off the trigonal planar bond angle. So this is going to be less than 109.5. And as you can see here for water, it actually is a little bit closer to 104 is the actual bond angle. It's obviously called bent or V-shaped because it looks bent. And I guess we dip it like that, you have a V, right? So there it is on that one. All right, so those are probably the geometries that you mostly have seen before, except for those couple of expanded octets. And because there's an expanded octets, there's two of them that we have, which there's 5 electron pairs and 6 electron pairs. Just like the rest of them, they could also have some non-bonding electrons on those as well. So let's talk about some of these geometries that we see for our expanded octets. So the first one we're going to look at here is something like xenon with 2 fluorines attached. And if we look at xenon with 2 fluorines attached, and we're going to go to our central atom here, and number of electron pairs, again, it has 1, 2, 3, 4, and 5 electron pairs. So just like we've seen before, something with 5 electron pairs is going to give us an electron pair geometry name of our triangular bipyramidal. But in this case, we actually only have 2 bonds happening. We have 1 bond there and 1 bond there. So the number of bonds are actually 2 in this case. So what ends up happening in this particular example is the 2 bonded atoms are able to find their way basically apart from each other in that linear arrangement. And that's actually what it is. It actually becomes back to linear, which is a different linear than the 2 and 2 that we saw at the very beginning. So again, you got to be careful of some of these things. This is a linear that is an expanded octet. It has a bunch of non-bonding electrons still there, as you can see here, that actually makes that triangular sort of geometry in the middle of it as well. So the molecular geometry here is linear. Electron pair geometry is linear as well. And in this case, the bond angle is actually 180 degrees, the bond angle, because it does make that sort of linear shot across there. And again, it's basically just going to end up like one of those guys, just kind of straight across, basically. And we will end up with those bonded atoms on the opposite side as far away as possible from each other. And again, that also allows our non-bonding electrons, as you can see there in that picture, to make that triangle sort of arrangement that keeps them as far away as possible from each other and also keeps them at a distance from our bonding electrons as well. The next geometry is also one where we have, as we look here, a central atom that has a number of electron pairs. 1, 2, 3, 4, 5. And again, that's going to give us an electron geometry, again, of triangular bipyramidal. In this case, we do have an extra bonded atom that we didn't have in the last one. So they're going to have to sort of keep their distance from each other, but we still have those non-bonding electrons that are also going to have to keep their distance. In terms of the number of bonds in this case, obviously we have 1 bond, 2 bonds, and 3 bonds happening. So these guys are going to be able to bond the electrons, kind of keep their distance. And again, they're going to also be able to kind of keep their distance from those non-bonding electrons that are there. And it creates a molecular geometry shape known as T-shaped, because I'm going to imagine it kind of looks like a T, right? So I think I probably did it off of this guy here. If I could do it. That is chlorine. Oh, which one's chlorine? Green. Oh, the yellow green. Green. Not that green. Have a bunch of holes. Or not. We'll steal this guy. It'll look like it, I guess. So do that. And do that there. Just kind of put whatever I'm in there. But we'll just go this way with it. So you can see, obviously, it makes our 90 degrees and our T shape there. It's actually just a little under 90 degrees, this angle. This is really not chlorine, for example, but it kind of gets the idea. So, and obviously we have our non-bonding electrons obviously coming out over here up on top. So our bond angle on this one is less than 90 degrees in this case. The next geometry is also going to see 5 in the central atom. And we'll take a look here. Number of electron pairs. We got 1, 2, 3, 4, 5. Once again, because of our 5 electron pairs, it's not going to affect the electron pair geometry name. So it's going to be triangular bipyramidal till. But again, here we have 1 extra atom that we didn't have previously. So that's going to kind of take up some room. We got 1 non-bonding electron. So they will end up in a molecular geometry that is known as seesaw. If you're old school, it is also sometimes referred to as a distorted tetrahedral. In case you come across some of that old literature everybody likes to read. I don't know stuff. So sometimes referred to as a distorted tetrahedral. But I think your book and most books nowadays roll with the seesaw. Obvious reason there is it looks like a seesaw, right? When you put it on there. So I think I can deal with this one. Hopefully my oxygen will not roll off the counter here. Right. What I got there? I got 4 bonds. So do that, right? So seesaw, yeah, back and forth, all that good stuff. So it looks like that. And obviously here we would have, in this case, some non-bonding electrons coming out towards this way. And it gives you that seesaw sort of shape. It has a bond angle of, come back, has a bond angle of less than our 120 that we had. And remember, this one had the 90 degrees as well. So again, we got sort of like a 90 degrees, a little less than, and also our 120 bond angle coming through here as well. Kind of that triangle type of situation. The next geometry, which is again an expanded octet as well, we look at something like xenon with 4 fluorines attached. Number of electron pairs here going to be 1, 2, 3, 4, 5, and a 6-pack there, right? So that's going to give us electron geometry of octahedral, right? Again, not affecting the electron pair geometry, the number of electron pairs. In this case, we have in terms of bonds, I kind of scribbled all over that there, but we got, and we'll go a different color here. We got 1 bond there, obviously 2 bonds, 3 bonds, and 4 bonds. Number of bonds is 4. So something with 6 electron pairs and 4 bonds is going to give us a square planar geometry. And basically what's going to happen is our non-bonding electrons will really try to stand on its head here and get as far apart as possible. And what that's going to do is basically make a square within the plane of the molecule. So we'll have kind of those non-bonding electrons up and down, and it'll make that square within the plane, hence the name, a square in the plane, square planar, right? So you got this basically square going on in this case. And obviously, because it's a square, you're going to have obviously a 90-degree angle happening right at our corners there of our square happening in that case. Lastly, which is the words you've been waiting to hear, the last geometry here is one where we have obviously another 6 electron pairs. And here, if we look at it, number of electron pairs around the central atom going to be 1, 2, 3, 4, 5, and 6. Once again, that is going to give us the same electron pair geometry of octahedral. In this case, we now have 5 things there along with our non-bonding electrons. So it's going to make something known as square pyramidal. And that one I think I could do. Bromine is orange. Why not orange? I like orange. That's not the good orange. Maybe. Or maybe I can't on this one. Maybe use this one. Maybe it will work. We'll see. So if we connect in there, let's try 5 and see how we do. Actually, maybe I'll just steal that one. See if we can make it work here off of this. Let's try this one. Better. Not enough holes on that one. Somebody needs to drill one more hole into this thing. All right. Well, doesn't look like this kid's got one that will work for that. So again, you can kind of see in this picture, obviously, it makes that sort of pyramidal shape on the bottom. And it's sort of a square as it kind of comes down and makes that pyramid shape. So square pyramid, 6 electron pairs, and also 5 bonds, not 6 bonds, but 5 bonds. 1, 2, 3, 4, and 5 bonds here for this guy. And that's going to have a bond angle of less than 90 degrees as well. So you can see here with the expanded octet and the exception to the octet rule, we do have a lot more geometries than you might remember from the previous class and our bond angles here. Here's a picture from your book or one similar to that that has pretty much this table. Best way to do it, since most people cannot visualize 3-dimensional space, myself included, is to electron pair. The number of electron bonds is really what you want to look at and sort of just know what geometries go with them. You are responsible for the electron pair geometry name and also the molecular geometry name as well. And again, you have a similar table in your books. It's not the one from your book, but you do have a similar table in there along the way. Now, to close out here a little bit on geometry here, what happens if we had, say, something like this? So let's just say we had an organic molecule such as this, and we wanted to do geometry for this. So how would we do geometry for this? We would basically do it for each central atom by itself. So in this particular molecule that I just drew there, we would assume that this would be a central atom, this would be a central atom, this would be a central atom, and this guy here would be a central atom. And basically, to sort of do geometry when you have multiple central atoms, what you essentially want to do is, obviously I can't do it here, but you essentially, for example, if we look at this very first carbon here, we just want to kind of put our hand over what I just boxed and pretend it's like not there. And we still, though, count the connection to it. So if we were going to do that carbon right here, it technically would have 1 electron pair, 2 electron pairs, 3 electron pairs, and 4 electron pairs. And in terms of bonds, it would have 1 bond, 2 bonds, 3 bonds, and 4 bonds, and it would have 4 bonds. So we know something with 4 electron pairs means it's tetrahedral for its electron geometry. And it also has 4 bonds, no non-bonding electrons around the central atom there. It would also be tetrahedral for its molecular geometry. Now, once you do that guy's geometry, what you essentially will do is move your hand over. And now what you're going to do is, if we look at the carbon next to it, we're just going to kind of put our hand over this guy and put our hand, over that part of the molecule. And we'll look at this. Once again, this counts and this counts for that guy as well. So this has 1 electron pair. This double bond counts as 2 electron pairs. And this one counts as 3 electron pairs. And in terms of bonds, this has 1 bond, 2 bonds, and 3 bonds here. So something with 3 electron pairs is going to be trigonal planar for its electron geometry. And also has 3 bonds, no dots on that central atom. So it would also be trigonal planar for its molecular geometry as well. Now, again, you just kind of keep moving down there, and we'll just do the last one here. We'll skip the carbon and the second to last there, and we'll just go to here. And again, we'll basically just kind of put our hand over that part of the molecule, and that's about all we'll put it over at that point. We'll look at this oxygen, and this guy would have 1 electron pair, 2 electron pairs, 3 electron pairs, 4 electron pairs, and 1 bond and 2 bonds here. And that is going to give us an electron pair geometry of tetrahedral because it has 4 electron pairs. Now it has 2 bonds and 4 electron pairs with our non-bonding electrons. That means that the bent or V-shaped would be our molecular geometry. And just to show you sort of what that would be, if you took this and we'll take this, and we'll put that right here. Do a little bond this way here. Here. And we'll just do this. This. And this. So if we look at this, basically what we would do if we want to do the geometry of this guy, we would do 1 electron pair, 2 electron, 3 electron pairs, 4 electron pairs, 1, 2, 3, 4 bonds. That's going to give us our tetrahedral geometry. We would then roll it over this way, and we would have 2 non-bonding electrons coming out here, and we would have 1 electron pair, 2 electron pairs, 3 electron pairs, and 4 electron pairs. That would be tetrahedral for electron geometry, but only 1 and 2 bonds. And as you can see, the bent or V-shaped happens there. So if you have multiple central atoms, basically just kind of hold your hand over the side you're not looking at, but you do want to make sure you include the bond and when you're counting it. Any questions on that there? All right, we're going to lay that up for now, and let's talk